As the burst fell back, the base surge formed, a heavily radioactive cloud of spray and mist which spread to nearly 1 mile in radius. A few seconds later, the detonation bubble collapsed. This caused a new plume to be thrust upward through the primary cloud. The cloud approached Bossell but did not cover her. These views were from the destroyer Preston. Other observers had different views. This is how the burst and shock wave looked from the A3D photo aircraft flying at 20,000 feet directly overhead. The technical photography from this portion has proved to be a particularly valuable source of information. And this is how it looked from another of the technical photography aircraft, an R5D flying at 10,000 feet, 6.5 miles on a direct line from surface zero. Performance of the 120 cameras used to cover the different technical aspects of this test was considered perfect. As the base surge spread to its full size, it began to drift downwind, a feature which has to be taken into careful account in tactical use of this weapon. Here is another look at the burst from the angle of a low-flying Yorktown helicopter. And this impressive view of the shock wave spreading across the water was seen by the crew of another helicopter.
The SPS-37 radar antenna is lost due to the failure of the lower plate section of the pancake aluminum casting, a part of the pedestal. The SPS-30 is tested to destruction in order to obtain comprehensive loading information. The reinforced pedestal of the SPS-43A antenna holds under the 10 psi overpressure, and the array survives without damage. The drums going over the side are the SPG-55 Terrier guided missile dummy directors. There is some damage to the ASROC launcher, but launcher operation is not impaired. There is no visible damage to the Mark 44 rockets loaded in the launcher. In the electronics installation on the forward Mac, the URD-4 radio direction finder and the SPS-10 are carried away due to bolt failures. The base structure of the SPS-42 is severely deformed. the blast side of the hardened deckhouse. Some longitudinal plating stiffeners sustain a 2-inch permanent deflection. There is no damage to electronics equipment in the CIC room. Observe the horizontal motion of the equipment. The after end covers of the Mark 32 torpedo tubes are blown off the port and starboard tubes. The Mark 44 and 46 torpedoes stowed in the tubes show no indication of damage. The dished skin of the blast-hardened deckhouse. The fiberglass deckhouse in the foreground is essentially undamaged. In the background, the tripod mast falls from the aftermath. The Mark 25 torpedo tube is severely damaged. The aluminum casting cracked at the foundation. Hold-down bolts elongated. The insulating blanket destroyed, and the muzzle door sprung. Despite the damage, the tube remains operational. Looking forward at the aftermath. The tripod mast carrying the electronics gear is destroyed and falls to the deck. Instruments detect some movement of the stowed missiles, but there is no observable damage. This SPG-51 Tartar-guided missile radar suffers no major damage, but minor failures put the equipment out of operation for 1 hour. Virtually the entire starboard side of the standard DLG-16 deckhouse between the O2 and O4 levels is blown in under 10 psi overpressure. Failure appears to have been caused by rupture of the deck-level welds of the vertical web frame. Another compartment of the standard DLG-16 deckhouse on the O2 level. The simulated bridge on the O3 level in the DLG-16 deckhouse. The significance of Operation Sailor Hat is summarized by Mr. J. Armstrong, Bureau of Ships, U.S. Navy, Technical Director of the operation.
Shot Delta concluded the airburst portion of Operation Sailor Hat. In addition to the projects directly associated with the ship evaluation program, various other projects were supported. These dealt with seismological effects, underwater acoustics, radio communications, cratering phenomena, free-field air blast measurements, fireball generation, cloud growth, and electromagnetic effects. Data obtained from the ship evaluation program indicate that the goal of greater ship protection can be met without imposing unacceptable weight and cost factors or sacrificing operational requirements. For example, Sailor Hat tests determined that although some radar antennas were incapacitated by blast, no new concept of antenna design is required. However, ruggedization of these items is required and can be accomplished by a planned and progressive blast hardening program. Analysis of all test data will result in better damage range and standoff predictions, as well as a more vivid appreciation of the effects of enemy weapons. Future analysis of Sailor Hat test data will provide design and specification information that is necessary to construct ships which will have a greater survivability in combat.
In flight, the pilot will select an arm position. At release, a pulse of current is transferred from the aircraft to ignite the pulse thermal batteries. The parachute is deployed. After parachute deployment, switches close to enable the depth bomb circuitry. The low voltage battery output rises to start the chopper motors. At water entry, the depth bomb timer is started and the parachute is jettisoned.
Stations control, stand by. Fire.
On certain ships, fire control radar is capable of tracking the missile in flight and displaying the water entry point on the geographic plotter. The missile reaches motor cutoff velocity. The motor separates and falls away. This preset velocity value determines missile range. At the preset separation time, the airframe separates. A parachute opens to slow the torpedo for water entry. The nose cone shatters and the parachute is released. The torpedo dives to the initial search depth and begins active searching. If it has not located the target by the time it reaches the preset floor depth, it starts up again, still searching. When it locates the target, the torpedo homes in on it. The procedures for firing a depth charge are the same. However, consideration must be given to safety of own ship from the underwater nuclear burst. No parachute is used with the depth charge. It drops through the water until it reaches proper depth. Then, ASROC, with its rocket motor and choice of warheads, provides an effective weapon against the extended capabilities of modern submarines.
This is the Mark 45 torpedo, an anti-submarine weapon with a nuclear warhead. After firing, the torpedo dives or climbs knots. It dives to a preset depth. A depth monitor function prevents it from diving deeper than desired. Burst range and course can be changed by wire guidance during the run. An anti-circular run function prevents it from turning back on the firing ship. At the burst point, the warhead is detonated.
The nuclear submarine force of the United States Navy is being equipped with a long-range, rocket-propelled, inertially guided anti-submarine missile, the Sub-Rock. The Sub-Rock is ejected from the standard 21-inch torpedo tube. The rocket motor ignites beneath the surface of the water, and the missile is programmed up and out of the water with the missile is controlled by a thrust reversal system that separates the rocket motor from the depth bomb. The depth bomb's underwater devastation will be furnished by the Mark 55 Mod 0 thermonuclear warhead. The warhead weighs about 460 pounds and has a length of 39 inches.